Hello everyone, welcome back to IJTCS 2021. This is the Young PhD Forum. Let's welcome our first speaker, Zehao. He is a PhD student from Department of Statistics and Data Science, Yale University. Previously, he obtained his bachelor degree from School of Mathematical Science, Peking University. He has wide research interests include statistics, optimization, game theory, machine learning theory, and reinforcement theory. Today he will give a talk about the learning in GAN. So let's welcome.
Hello everyone. Today the topic of my talk is making method of moments great again. How can GANs learn distributions? From this title, we can see that I'm going to talk about the connection between the method of moments and the generative adversarial network, which is a very famous generative model. And this work is done by Professor Yuanzhi Li from the machine learning department of Carnegie Mellon University and me. I am from statistics and data science department of Yale University, and I am currently a first-year PhD student. First of all, we are going to introduce a very simple generative model, which is the autoencoder. Of course, this is not that simple, but simpler than the generative adversarial network. Okay, in the autoencoder model, we have an input and we have an output. They are of the same dimension. They are both pictures. We input a picture into this network, and by using the encoder neural network, we can compress the input picture into a low-dimensional code, and then we use a decoder neural network to convert the low-dimensional code back into a picture. And the loss function of the autoencoder is to make the input picture and the output picture to be as close as possible. As we can see, for every input pictures, we use the encoder to compress it into a lower dimensional space, and then we depress it into the original high dimensional space. Through this process, we can preserve the effective information of a picture and erase some noise. This is the autoencoder. And yeah, by making the input picture and the output picture as close as possible, this generative model is always used as a cleaner or eliminating the noise. But for the generative model autoencoder, there are some problems or there are some shortcomings. For example, look at these two pictures. In the MNIST model, if we pick this picture, which is real, which is from the real data set, this is a number 7, and look at this picture, this is fake. Although these two pictures are have only one pixel difference, but the right picture have a dot here, and it is obvious that this is not a real picture. This is generated. From this example, we can see that sometimes, although the realistic one and the fake one does not have so much difference on the L2 difference, but through the observation of human beings, we can clearly and easily tell their difference, and we can say the left one is real and the right one is fake. It means that there are some ways to improve the existing generative model autoencoder. We can use another loss function to improve the generative model and the generated outputs, so that we can it will be harder for us to tell the difference from the realistic one and the generative one. So For the new model, we use another input method, which is the unit Gaussian. We input a noise, and through a generative model, which is usually neural nets, and we can get a generated distribution, which means we are going to learn a super complicated G, generative model G, and when we input a noise Z, the GX can become a very good output picture, a very realistic picture, and we are going to make G to be our generative model. But after we get the generated distribution, how are we going to design the loss function so that we can try our best to make the generated distribution as close as possible to the true data distribution? As we know, all we have is some special data points. For example, the MNIST data, the bedroom data, or the CIFAR-10 data. They are sparse points. They are not a continuous distribution. So we are going to figure out a way to design the loss function to make the generated distribution as close as possible to the true data distribution. And here is when the Wasserstein GAN comes. In the previous picture, we are going to design a loss function from the PG, the generated distribution, and the P data, the true data distribution. And here we are going to introduce the Wasserstein distance, which is a perfect distance to measure how close two distributions are. For example, for two distributions PR and PG, this equation is the famous Wasserstein equation, and the second equation is the Wasserstein distance, and the second equation is a special case of the Wasserstein distance, which is known as Wasserstein 1, W1 distance. As we can see, if PR and PG are the same distributions, then the distance is obviously 0, because for any function f, the expectation over PR will be exactly the same as the expectation over PG, since they are the same distribution. Of course, if PR and PG are not the same, they are somehow equivalent. The distance would also be 0 under some condition over f. So here we have a constraint that the Lipschitz constant of f should be upper bounded by k, which constrains the gradient norm of f. And by using this Wasserstein 1 distance, we can figure out a way to measure the distance between the generated distribution and the target distribution, which can be converted into an optimization problem. But this is not an original optimization problem. This is a min-max optimization, because we are going to minimize over all possible generative models G and max over the discriminator, which is the function f in the Wasserstein distance. For every G, we are going to find a D which maximizes this gap and calculates our Wasserstein distance. This is why we max over D. And then, since every G has such a distance, we are going to minimize this distance. So we minimize over G, and then we maximize over D. And we name G as generator and D as discriminator. So the discriminator means we need a judge. We need a judge or a teacher to see how close is the generated distribution to the target distribution, or how much can we discriminate between the real pictures and the generated pictures. For example, At first, the generator is very poor. Yeah, in the early stage of our training process, the generator is very poor, and our discriminator can be very easy to discriminate the real ones and the fake ones. But when our training becomes goes further and further, our generator becomes better, and our discriminator also becomes better because it can tell the difference from some very realistic generated pictures and the real ones. So for the Wasserstein-Gahn, there is a main question, which is when the training stops, whether the distributed distribution will actually be close to the target distribution. And question 2, how can the training process reach to such configurations efficiently? Yeah, since it is not a minimization problem, this is min-max problem. So it's hard to say when the training should stop. We don't have a 100% accuracy. What we have is only a number. It's only a distance. Yeah, and as we know, in each iteration, it is impossible for us to find the optimal D and then take a step on G. What we can do is to take some steps on G and then optimize on D, and then G, then D. Yeah, we take turns to do the min step and the max step. So it's hard to converge. Yeah, it's hard to converge. This is the first problem. The second problem, we don't know where will this optimization algorithm converge. Maybe it does not converge, but if it converges, where would the converging point be? Will it be the point where the target distribution stands for? Yeah, this is a very important and essential problem for Wasserstein-Gahn. From some simple experimental results, we can see that through the training process of Wasserstein-Gahn, our first order moment, second order moment, up to the sixth order moment will converge to 0, which means when the training process goes further and further, the moment from the first order up to the sixth order of our generated distribution will be closer and closer to the moments of the true distribution. This is a successful training, and all the orders of moments get close to 0. But if a training process fails, then the orders will become random. It will not converge to 0. It will be higher than the baseline. For the existing works on the theory of Gahn, there are many famous papers. For example, by the Sanjeev Arora group, by Teng Yu and Andre group, there are many very high quality papers. For example, generalization and equilibrium in generative adversarial nets, and Dugan's random distribution, and approximability of discriminators implies diversity in GANs, yeah, and so on. These papers answers the question and bridges the gap between the convergence analysis of GAN training and the quality of the final solution. Yeah. Although they cannot strictly guarantee the convergence, and also they cannot strictly guarantee the quality of the final solution, but they somehow bridges the gap between them and build some connection between them. For these two papers, we can see that during the earlier phase of training a neural network, the network is capable of learning a special class of functions. Of course, when we say these two papers, we are talking about the supervised learning problems, not the generative adversarial network. So for the original supervised learning methods, our network is capable of learning a specific class of functions during the early phase of training, which is the class of low-degree polynomials. So we can simply think about some connections between them. In supervised learning, the neural networks will learn the low-degree polynomials at the early stage. So we may ask, in the Wasserstein-Ganz training, whether the generator network or the discriminator network will tend to fit the low-degree moments at the earlier stage of training. Yeah, the low-degree polynomials and the low-degree moments, they are perfectly fit with each other. It means for the small number c, like 2 second-order moment or third-order moment, if our generated distribution and our target distribution will fit the lower order moments at the earlier stage of training. Yeah, this is the main problem we are going to solve or partly answer in this paper. Our work focuses on the Wasserstein-Ganz. In this model, the set of all functions is replaced by a set of discriminator neural networks. As we see, the Wasserstein-Ganz training objective is like this. Here, the G is the generator and D is the discriminator. And since omega is sampled from S, which means the standard Gaussian, so G omega would be our generated pictures, and X is our real pictures, our data sets. So by maximizing over D and minimizing over G, we can get our Wasserstein-Ganz training objective. So in this paper, we focus on the realizable case where the distribution D star is realizable by a 2-layer neural network. Look like this. Actually, this is a very useful and widely used assumption, because if we want to do something theoretical, we have to assume that the target distribution is actually realizable by a 2-layer neural network. Otherwise, it may not converge. We may not get what we want to get. Here, H is an activation function. It may be ReLU, it may be hyperbolic tangent, it may be some other functions. But in this paper, we are thinking about some special activation functions, from the polynomial functions to the more general ReLU functions. Here, alpha and V are trainable parameters, and we consider our discriminator network to be a ReLU function. So the main theorem of our paper says that for every smaller constant R, which stands for the lower order moment, if H is a degree P polynomial of Z, here H means the activation function here. If our activation function is a degree P polynomial, then given these numbers of training examples with high probability, our generator network would fit the lower order moments of the true distribution in this convergence rate, which is the poly over epsilon over n0. Here, the n0 is the number of training samples. For every generator network, such that this inequality holds, we must have that the generator actually close. The generated distribution is actually close to the target distribution under the Wasserstein-1 distance, which means if our moments are close, then actually our distribution will be close. Here, we only need the lower order moments, which is a very important and a very big result, because intuitively we need two distributions to have very close moments, or each and every order moments, to make sure that these two distributions are close to each other. But actually, by using the Wasserstein GAN and using the two-layer ReLU network, we can guarantee that once the lower order moments are fixed, or are fully trained, then our generated distribution will be close to the target distribution under Wasserstein-1. By using simple numerical experiments, we can see that if our discriminator functions are quite easy, like linear, then the Wasserstein loss and the parameter distance may not even converge. But if we use more complicated discriminators, like quadratic ones, like cubic ones, or even one-layer ReLU and two-layer ReLU, our Wasserstein loss will converge to zero very quickly, and the parameter distance will also converge to zero very quickly, which means when we converge our Wasserstein loss to zero, the parameter is actually the same or very close, which means our generated distribution is actually close to the target distribution. So to prove our main theory, we are going to start with some simple scenario, which is the cubic generator scenario. So what is the cubic generator scenario? It means that our activation function h is not ReLU, it's not a higher order polynomial. It is just a third order polynomial. It is just z to z cubic. Here we denote G and G star to be the learner generator and the target generator, written in the following form. It is a two-layer neural network, but our activation function is a cubic function. Here we assume all the vectors vk and vk star are also normal vector groups, and the weights of the ground truth generator alpha k is positive. Actually, this is free to be assumed, because if alpha k is negative, we can put the negative sign into the cubic, and we can give it to the v. Here, the input vector of generators omega is drawn from the normal distribution, normal Gaussian distribution. So under some assumption on the parameter alpha k's, we can strictly prove that for each component mi, for each component of gk and gk star, if their lower order moments from the second order, fourth order up to the 2R's order moments, if their lower order moments are perfectly the same, they are perfectly fitted, then then we can say that the parameters alpha k and alpha k star, they are exactly the same. They are equivalent over a permutation operation. We name it intro component moment analysis, because we only compare the lower order moments of a single component. The next step would be intercomponent moment analysis, because for Gi and Gj, which are two different components of G, of the output of G, then by calculating the intercomponent moment, Gi to the power of k times Gj. Here, k can be 1, 3 up to double kr minus 1. For lower order k, if these two set of moments are perfectly the same or perfectly fitted, then we know that the vector group vi and vj, their inner dot, their inner product is exactly the same as vi star times vj star. Yeah. With these two theorems, theorem 1 and theorem 2, we know that if the learner generator G and the target generator G star, if they have the same lower order moments, then we know that their alphas will be the same. Their vectors V will be equivalent over a rotation. So we can conclude that these two generators are exactly the same. So in the next step, we are going to discuss something more practical. Yeah, since our number of data points cannot be infinite, we only have finite data points. Like MNIST, we have 60,000 data points, etc. Yeah, so we cannot accurately compute the moment of the target distribution. We can only compute the empirical moment of target distribution. So there is an error here. Yeah, the moment of Gi will have an epsilon error with the moment of Gi star. So the question is, how many data points do we need? What is the sample complexity in order to make these two distributions as close as possible? In order to make these two distributions to be epsilon close, how many samples do we need? To answer this question, first we study the intro-component moment analysis, of course with some kind of errors, and if we list R equations, the ith order moment of Gk equals to the ith order empirical moment of Gk star, then after solving these equations, our alpha k's and our alpha k stars will not be the same, but they will be very close to each other with this error. Although it will be large, like polynomial over PER, blah, 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 over to the power of polynomial PR, but for the sample size n, it is the 1 over squared n order. This is the intro-component moment analysis. Then it's the intercomponent moment analysis. So for these KR equations, if we cannot accurately calculate the accurate moment of target distribution, we can only compute the empirical moment. Then there will be an error. There will be an error upper bound, and we can easily compute. The inner product of Vi times Vj is close to Vi star times Vj star over this bound. And after we connect them together, we get our main theorem, which is the G push forward Gaussian, standard Gaussian, and the G star push forward standard Gaussian. The Washington 1 distance of these two distributions, which is generated one and the target one, will be upper bounded as this. Here we finished our talk. From this main theorem, we can say that if we have polynomial number of data points, And after we fit the lower order moments of the target distribution and the generated distribution, and we can say that these two distributions are actually close to each other. Not only their lower order moments are close to each other, their higher order moments will also be close. Their Watson's distance will also be close. If you want to see the complete version of this paper, you can just search the name of our talk, and you can search the name of our talk and search on archive, and you can find our paper very easily. Thanks so much. Thank you for your coming.
Thanks again for the host wonderful talk. And due to the time limit, I think we don't have time to answer the questions. If there are other questions from audience, maybe we will let Zehao knows, and his answer may be posted in somewhere in the living room or some WeChat place. And so this is the end for the first talk, and